Yeah, Vishnu, you're normally in Canada, you're back in India right now. I think it is a good start if you can tell us exactly what brought you to Canada, how you got into tech, and what you're doing right now.
Interesting. So I don't remember a time when I'm not in tech. So it's 15, 20 years I've been coding. I've been programming since, I don't know, 8th grade. But my entire degree, my undergrad, master's, everything in software engineering. So I'm not a data scientist by discipline. And that's probably what I'll bring to the MLOps community as well, right? So there is a set of wisdom that is coming from the software engineering world that's very relevant to the MLOps community in general. And how we built our deployment patterns, how we built our pipelines. These are largely a mesh of data science workflow combined with traditional software engineering paradigms and wisdoms. So that's what I bring in. That has been what I've been working on for over 10 years now. What I do right now, I lead a team of data scientists and engineers at Innovyze to solve a very cool problem. We work in the water industry. Obviously, like we build the freshwater supply for the world is limited, like extreme weather, flooding around the rise, and the demand for like freshwater has grown dramatically, and our capacity to deliver them is limited to a growing population safely, affordably, reliably. Right. So this is where Innovyze comes in. Right, we built all the software that makes water infrastructure happen, in simplest words. But this is one of the legacy industries, and we have our own problems. Like there is aging infrastructure. Some of these pipes and assets that I work with are like 100 years old. Right. So like, there has been an instance where we actually dug up a wooden pipe. And like if you're modeling the vibrational characteristics of a wooden pipe, it's completely different from like a regular pipe. So you can imagine the kind of data science problems we go through just because of this aging infrastructure. Right. The workforce that is operating these distribution networks or wastewater management plants, they are all like largely retiring. It's baby boomer generation. They have this tribal knowledge that has been built over decades. That's not translated well into the next gen, right? So there is a lot of scope for automation. So this is like we are coming in at the time where this industry is starting to consider automation, right? Like many of them have, but there is still like a trailing large list of people who have not moved to cloud or bought a SaaS product, for example, or the security model is old, things like that. And well, I try to solve, and this industry comes with its own unique set of data challenges, its set of quality problems. As I told, wooden pipe problem, right? So these are the issues that we deal with every day, and we have built a solution to optimize and solve all of these things that we talked about.
So what are
I lead a team.
Yeah. What are some of these use cases that you're working on? I mean, there's the wooden pipe, but you said that you make basically the fresh water happen. Is it just around the infrastructure, or are you purifying it also? What's going on there?
Right. So that is an oversimplification, but Innovyze is exclusively a software company. We largely build digital models. Like the term digital twin is familiar to many who are working in the industry. It's basically a virtual representation of these physical, actual, tangible assets, right? So if there is a distribution network that takes water from a lake, pumps it into a reservoir, and maintains like a certain level of pressure, and then it supplies to people's homes. So we call it a water distribution network. In reality, there is way more pumps, way more lakes, way more reservoirs. But ultimately, there is like an aggregate demand, which will be like a curve, right? So there is people are waking up in the morning and they will require X liters of water, but as the day passes, it reduces. So there is like a demand curve that we need to meet. All the while, there is a tariff distribution to the electricity that these companies are using to pump the water in from the lake to the reservoir. Right. So the first thing we do, we take this network, we digitize it, build this digital twin. And what it means to be digital twin is we can virtualize its operation. So we can input certain way the pumps should run over the next 24 hours, and we can see whether it will meet the demand, how much energy we consumed in doing that, right? So Innovyze, at least my org, then basically optimizes this operations. We provide customers with a schedule of how to run their network or their system in a manner that will save them energy cost, optimal, right? So all these problems I talked about with aging, like operators and all of that goes away by adding like an AI-based automation into this. The actual details of how that works is a fairly involved discussion. I can get into if anybody's interested. Yeah,
well,
but it involves. Yeah, go ahead.
Let's talk a little bit about the platform that you've built for data scientists and the whole machine learning. And so maybe we can talk about some of the, like where you started when you got into it, and then how it's evolved, and what does the platform look like now? Why is it unique?
All right. Yeah. So like I just told, right? So there are certain problems that comes as part of the territory working in this industry. First, sensor placement is bad, right? These are old, unreliable sensors placed across this network. But some of them are reliable, but not many of them are. There is a lot of sensor anomalies. And another issue is that the data is very sparse. Like some of these chemical concentration, some of these measurements of quality of water is taken like using manually collected by a human being every day, sent to a lab. After X number of hours, the results come back, and this is your one data point in the time series. Wow. Right, so you get 4 of them a day, and we need 20,000 of them a day to build reliable models. Right, so these are like unique challenges that comes with working in this industry, and we by large we started out to figure out whether there is a way to even like build a digital twin, build a reliable representation of this network, because the data is so bad, right? So we figured it out, but that goes into our IP. But the MLOps and the AI pipeline, where it really helps is it kind of enables this configuration-driven data cleaning and data transformations and feature engineering that you apply on these data points, consistent and reproducible like across various other points in the pipeline. So let's start with somebody building models in like a Jupyter notebook, applying certain feature engineering transformations and data cleaning operations. They're dropping, interpolating data, they're dropping sensor anomalies, and we apply a lot of them, right? So this needs to be reliably replicated in real-time pipeline, in batch inference, in retraining, right? So like a config-driven, there's like a config-driven element to that we need to build. So when we started building it out, like this is handcrafted models, and they were working in theory, but it never materialized in production, like when we started with our first customers. So that's the first time we're thinking about MLOps. How can we solve this problem? the first thing we started doing, we started building like a model repository kind of thing where we can build and deploy the models along with this associated metadata that talks about how feature engineering was performed, how data cleaning was performed. And we tried to reproduce that in real time, but it turned out a lot of like manual custom building work. And we tried a few other out of the box solutions, Data Robot, Data IQ. There are a few providers out there that claim to provide an end-to-end solution to this problem. But ultimately, we kind of built a bespoke solution, which is kind of the MLOps that everybody has, right? Nobody has a,
totally.
There's no standard MLOps package out there that works for everybody. It's always bespoke. But we leverage Stagemaker and Amazon AWS to do a lot of these building blocks. And it's still a work in progress, but we right now have a decent deployment pipeline that involves the end-to-end data science workflow, starting from feature engineering all the way cleaning, all the analysis you need to do, ability to do a continuous retraining. And we are reaching a point where we can do automated retraining. That's good. A CI/CD pipeline that promotes the artifacts from like a development environment to QA to production. And in between all the checks and balances you need, you get real-time monitoring in production. All the sweet stuff that comes with the all the sweet stuff that comes with a good MLOps pipeline.
Can you walk us through some of those, like that pipeline architecture that you're talking about, and obviously verbally here, but talk us through. And also, I'm really interested about why, when you did a POC with some of these other companies that you mentioned before, it didn't work out. What were some things that, and then you said, all right, well, let's just do, and you landed on Stagemaker. Why did that one work and the other ones didn't?
Well, let's start there, right? So there is really like two patterns out there. And I want to call it cloud agnostic and cloud native. It's the eternal debate in the industry, which way to go. People take both sides, but I'm generally a big fan of a cloud native solution. So, and Amazon, AWS is big, obviously the largest provider, bigger than next three providers combined, right? So Amazon have a large like array of tools that facilitates MLOps. That the idea is built around like a centralized IDE, integrated development environment, that it's like your Jupyter notebook, but it's just better, right? It's just connected to everything Amazon. So if you wanna do feature engineering, like if you wanna do, say, feature selection from a list of 200,000 features, your local machine that you're running the Jupyter notebook in isn't just powerful enough to do that. You can outsource that to Amazon's one click. You can do training, highly parallelized neural networks training in Amazon's compute cloud, another one click. You get APIs to do all of that. And then from the CI/CDs also, there is a Stagemaker pipelines to do reproducible training, right? So once data science is a messy process, right? Once you get to a good model, sometimes you lose track of how you arrived there, right? So it's important. It's important to be able to reproduce that, and we always like redo the whole thing, starting from raw data. All transformations that you applied get saved in a config-driven manner. It gets rebuilt and trained. In addition, you also get some free hyperparameter tuning in that environment, but ultimately the model gets rebuilt, and the artifact that gets rebuilt is what gets used in in production from now on, right? So a lot of these nice, cool things came with Stagemaker. Like, and alternatives, like if I were to go in cloud agnostic approach, and which a lot of people do, right? And there definitely is value to it, not denying that. It's just a lot more DevOps. Right? Data science is a very multidisciplinary process. As a result, there is several tools involved in it, right? So there are open source tools out there that do one thing really well, like DQ does unit testing for data, MLflow does experiment tracking, Jupyter Lab does like a shareable notebook mechanism, CI/CD has Terraform and 200 other ways of doing it. All of these are separate tools. Now, how do you bring all of them together? Like, that's a full-time job, right? So, and by going like cloud native, picking up tools that are built within Amazon and Stagemaker, you're basically cutting short all of that. You're way more agile. You're way more fast in figuring out it's business speed, basically, right? You reach your value point faster. And like, if you want to fail, like, MLOps is still an evolving discipline, right? Not many people have figured it out. So you need to try and fail many times before you figure out what's right for you. So this enables you to fail fast. Right? You don't want to figure out after maintaining and buying a huge Kubernetes cluster, even if it's in cloud, paying it for it after 3 months, then you realize that it doesn't work for you, right? So serverless patterns, things like that keeps your cost minimum, and while enabling you to build your custom bespoke MLOps pipeline faster than typical.
So can you talk about why you didn't go with open source tools? And I see there's a question that came through, so I'm going to get to that next. I promise I will get to it. But I'm wondering about like open source and if you played around with anything in that arena.
There is open source alternatives for everything we do, and to be honest, like a lot of these cloud providers leverage those, right? These are all I think SageMaker experiment tracking is built around MLflow, but I'm not 100% sure about that. But the cloud providers largely leverage open source tools, right? So the question is whether you want to do that integration yourself or let the cloud providers, in our case Amazon, do it, then use it. Right? So we did evaluate a few of them and realized that there is value in it. It's just that when we started evaluating Amazon, we realized that I can hire one less DevOps person to build and maintain this entire pipeline.
Yeah, that makes sense. So question coming through is, what's the platform that you're using to virtualize the physical system, that virtual twin?
Virtualize the physical system. So that's, without going into too much in details over IP, it's basically modeling each asset involved in this network. Let's say I talked about a lake and a pump and a reservoir and people supplying, getting water from it, right? So we model all of these components. And the model that you pick for each asset depends on the type, class of asset. A lot of them are random forest models. Some of them are neural networks. Some of them are autoregressive models that forecast demand, for example. So, but they are semi-AutoML style pipelines that allows you to pick the right model that solves that particular asset problem. So a pump is probably the simplest of this list of assets, right? So it's, if your pump is on, based on a pump curve, you need to determine what the flow is going to be from there. But as you add chemical process into this flow collation aeration, it gets complicated and there needs to be advanced models. But ultimately, we model all of these individual components using an array of machine learning processes and build a connected DAG, direct acyclic graph of these models that essentially becomes a digital twin. So now how in terms of the platform that is used, it's entirely in Amazon Stagemaker. We use various libraries that is some of them natively provided, some of them we developed for certain type of assets. But ultimately building models that represent these assets gets deployed to Stagemaker inference engine. And we leverage real-time and batch inference capabilities provided by Stagemaker, along with a custom-built framework on top of it to build this DAG. I don't know if that answered that question. If that doesn't, please follow up.
Yeah, that was pretty clear to me. I'm wondering about the data quality issues that you mentioned before, and how you have people, like, this scenario is wild to me. You have people manually taking the tests, and then you get 4 of them a day, and really what you would prefer to have are 20,000. So how are you attacking that problem? Are you just going in and trying to lobby for more sensors to be put in, or like what can you do there?
Well, not all data science problems are solvable, right? There is a degree of science in it. You can't rush it, can't solve it. But there are instances where we were unable to model systems purely because of lack of data. But there are really some really cool methods we have developed that helps mitigate this problem as well. Like, there are methods of building virtual or soft sensors that rely on the sparse data, but also leverage one of the other sensors that has more frequent data points to build the soft sensor. And there are some proprietary algorithms in doing that. But this conversation is not about data science, right? So in terms of MLOps, what we really need to do is enable data scientists to do whatever they want and make sure that it's reproducible in a pipeline. Like, that's the key, right? And this what I call as config-driven data transformations, mouthful. It needs to enable the messy data science process of building good quality features that go into a model from like a bad raw data, and capture that in the configuration, make sure it's available for retraining, make sure it's available for real-time inference when you want to do the predictions, make sure it's available for other batch predictions if you're doing any. Right, so that's one really good way. A robust MLOps pipeline helps in solving this problem, but the actual way of solving it itself is extremely data sciencey.
So this idea of reproducibility is obviously really important to you and the team. Why is that? Have you had problems in the past where you couldn't reproduce something and then it came back to bite you? Or is it just something that you're bringing from the software development world?
Well, reproducibility is obviously important for everybody, right? And most of the frameworks out there do that for you. There is, but it really starts from like the feature engineering and onwards. Like, the cleaning and preparation steps that involves calculation of calculated virtual sensors, calculated virtual channel streams of data, or dropping sensor anomalies. Reproducing all of them reliably and correctly between environments takes like a bit of work. It's a little bit of software engineering. There are tools out there that does that right now. Like Amazon itself has feature store. It goes all the way up from, I don't know if it does cleaning, but cleaned, go some raw data. You'll be able to build and store and save features that you can reuse across your multiple modeling exercises.
Yeah, that's a fascinating one for me, because I know in certain sectors, reproducibility is a must. right? Because of the law. And so it's really interesting to hear that for you, reproducibility is there because you just need to, it's like the core business, I guess, is what it sounds like. Like if you can't reproduce it, then your core business is not going to be able to work. Is that what it is?
That is what it is, along with the deployment pattern that we need to follow. Like, so one thing I might not have mentioned well is this digital twin building exercise is custom for every customer. Like they have different, some of them have wooden pipes like we talked about, but they have different networks, different assets, different problems. So there's a hand-curated exercise of building models. So it's not a separate CI/CD pipeline that is built per customer. It's one MLOps pipeline through which like a models pass through. Right? It's not like a CI/CD script that changes between customers, and you have the ability to customize it any way you want. If the day you start giving that kind of flexibility, your inference framework needs to change as well, right? The software that uses this leverages this prediction will need to change as well. So we needed to build like a certain degree of standardization around this process, which and there are like hundreds of models passing through this pipeline as well. So yeah.
So does that mean that it's like you have various customers and then these models are all going out, but each model is individual to each customer?
Yeah, largely so. Right. Yeah. The digital twin is built for the customer. It's somewhat hand-curated process that represents each customer's network, and they all have unique challenges. But the model types, right? So once you solve a model for a pump, like, and I'm picking pump here, it's a common simplistic asset here, but a pump is 200 types, right? They all have different characteristics. The model that you build for a pump typically works across. And you see like different pump curves mean you need some degree of tuning and optimization. But when it comes to other chemical, biological processes, and when these assets work together in combination, like each customer are really different, right? They have different models built to represent the digital twin.
So sticking on this reproducibility, just for one more, not to beat a dead horse, but I know that the idea of having the data, which is changing and it's constantly in flux, and then you need to go back and you need to try and reproduce that, can be difficult sometimes. How did you go about solving that problem?
So in terms like reproducibility applies to the process of the entire pipeline, right? It starts with let's say you collected some historical raw data that was in a customer's email somewhere, right? They emailed it to us or put in a Dropbox, we started modeling. In real time, there is also this data being collected directly from sensors and coming through a separate pipeline. Somebody who is starting to build machine learning models for this digital twin starts working on historical data, and he or she needs to connect this real-time data to this historical data to build models that works as one continuous stream, right? And this all works. Like all of this happens, they somehow make it work. It's just that at the end of building this, they lose track of what exactly happened, how we made it work. Right? There is this data doesn't. These units have changed between historical and real time, or they added a new sensor in in between these two time frames, or some other thing has happened, and there is like discrepancies between this data. So in terms of data, what you really need to do is provide like a centralized repository to do training, like for both real time and historical data use cases, and make sure it's one stream of connected data. And now this is really like an IoT style problem, IoT time series forecasting style problem. Not every industry has to face this, but we do. But and in time series forecasting, this is a fairly common issue. Now, the exercise of model building, once the data scientist goes and builds this, it's important to rebuild it in a separate environment, just to make sure it's not like a random stroke of luck. One, there are like compliance requirements. Sometimes there is transparency, like model understanding requirements. People asking why is it predicting this way, right? Things like that. But more importantly, retraining, right? So as time passes, more and more data becomes available. It is by the nature of time series forecasting, and models can do better. Or in other cases where there is like a concept of data drift, right? So 2020, for example, was a completely different year for everybody. It basically broke many time series forecasting models out there that dealt with real-time data. So in our industry, like water, rainfall patterns changed. A lot of things changed because people's behaviors changed during COVID. And essentially all the models built before 2020 became obsolete, right? So retraining solves this. Like real-time automated retraining solves this. Now it's extremely hard to do, but reproducible training is like a step one to attaining automated retraining.
And I want to talk about the automated retraining in just a minute, because I also find that idea fascinating on whether or not we should be doing that and how we go about doing it. But I wanted to ask before that about the data scientists and their workflow, and how I know that you have a few data scientists on the team. So how do you enable them to collaborate?
Yeah, so I don't know if others have figured this out, but data science workflow is a messy process. It's and it's in the nature, right? It needs to be that way. Like we need to enable that, as opposed to drawing a box around that process and saying this is how you have to do it. Right? So I have found that it's a creative process. It's a it's over and over iterating over problems. Like we had problems, models that we were unable to build for months, and a third person was looking at it and something clicked, and then the model got fixed, right? So but how do you enable this? If you have, we started out with local Jupyter notebooks running on people's laptop, right? That's obviously a horrible practice, but I think that's how many data science projects starts. Now, how do you enable sharing, right? How do you give this to somebody? Jupyter Lab and today's notebooks makes it a lot easier, but still it comes with, you can't just do an entire 2,000 line data science process and give it to a person like in a Git and then make sure it click run. It never runs. It fails. Like I almost guarantee, right? So there are data structures in memory. There are things that are saved and stored and configurations generated. These all needs to be shareable, right? So I can't claim to have figured out that process, but we have taken steps, right? So Stagemaker Studio enables sharing without compromising security. So another issue with sharing is that you have a 20-person team, and sometimes we have contractors to extend our work. There is security requirements there that you absolutely need to meet. The data needs to stay in certain regions. Certain set of people who have already signed the contracts are the only ones who have access to NDAs, are the only ones who have access to it. right? So if you have a centralized Jupyter Notebook server, everybody has access to everything. Like you can't do that. Right? So there is permission issues that you need to figure out. I'd say like Stagemaker Studio as an IDE does a reasonably good job of solving this. The reproducibility of a 2000 line Jupyter notebook that we just talked about, that's not exactly solved. It still has issues to figure out. But I think soon enough we will see that somebody has answers to that question. Like I need to know right now, but in a few years, I think that's a process that will evolve, mature, and it'll change. It's changing. Even the last 2 years, the way data science is done in a notebook as a team, that process is changing.
And that's something that comes up in the community a lot. And I know if anybody here wants to chime in, we've talked about it so much. Are Jupyter notebooks for production? Should we just like not even think about trying to bring the Jupyter notebooks into production? So let us know if you have any opinions or thoughts on that. There's a great question that just came through that I want to highlight. And this is one, I imagine you've got a few, considering you've been in tech for so long. Ideally, one around MLOps, but you can tell us other war stories if you want. So Vishnu, do you have any cool war stories you can share with us? Anything, maybe model quality or model deployment failed and it was a complete disaster? And what did you learn from it?
I need to pick one. There
are many.
Every day. It's every day, right? Well, I'm just going to go with one of the top easiest ones and came to my mind. Like we had this South American customer who had this particular data sparsity problem. There was we were basically improving the effluent quality. And what that means is that wastewater that goes from your homes gets treated and sends back to like a river or a lake. And there are governmental compliance requirements on how the quality of water should be. Like there are certain chemicals and certain concentrations, right? Now, this is one of those things that gets measured manually. And in this particular case, it is extremely manual, once in a day process that somebody drives down to this location, collects this data, sends it to a lab. 2 days later, you get the result. Then they enters in their like an Excel sheet somewhere in there, and then we get the data point 2 days late. Meanwhile, our system is trying to optimize this in real time. Right. So this is a problem that we presented, but we were way earlier, like a startup at that point, and it was a big contract. But we tried to solve the problem, right? There are creative ways, like we talked about building virtual sensors that can correlate to like other data points that do have real-time data, and then build like a virtual way of representing this effluent quality thing. But ultimately, the lesson I learned was that some data science problems are not solvable, and it really depends on the data. Like the industry, and that it seems so trivial right now, but it was a very expensive lesson. Right?
Go ahead, finish up.
Yeah, we spent man hours, and I don't even want to talk about the expense in trying to figure out the answer. We learned quite a lot from it, right? It helped in many of our customers that came after that who had the same problem, but not as bad, right? But it's the resolution of this data that really caused this issue. But the technology that we kind of experimented and built for this customer was helpful in solving some of the other problems, but this particular one simply didn't work.
Well, so you were saying that you could solve that problem, and then at the end of the day, you couldn't. Is that what happened?
Yeah,
because
that's exactly
the quality was so bad.
Yeah. So some models are not. You can't build it.
Yeah.
Data quality.
No matter how how presumptive and arrogant you think you are, it's not going to happen.
No matter
if you
what
don't
you
have
throw,
the data,
latest neural network at it, you don't have the data, you can't build it.
Oh, that is amazing. So that's something that it reminds me of a talk that I had a few months ago, and one of the people that I was talking to was mentioning this idea of techno solutionism, I think is the name of it. Somebody can correct me if I'm wrong, but the idea is that every problem can be solved by tech, and it's a little bit of an arrogant idea that every problem, I mean, this problem potentially could have been solved by better tech if you had more sensors and you had all of that. But when I was talking to someone in the, when I was talking to this person, they were talking about, you know, when it comes to bigger issues like mental health, should that be solved by tech? And so that's a bit of a tangent. I know we just went way into left field for everyone, but it reminded me of that because it's one of those where you say, oh, we got this under control and we can figure out what the problem is and we can throw a neural network at it and we'll be able to like solve this. And then you realize, wait a minute, if we don't have the right data and if we only have once a day data and we're trying to solve this in real time, but our data is lagging by 3 days, that is a problem that is, it's very difficult to argue that that can be solved no matter what kind of data scientist. You can have the best data scientists in the world on that, right? So that's a great one. There's another question coming through in the chat. How would you know if the data has the information that will help you to predict what you want or not? Do you have pipelines to analyze it first?
Well, that's a great question. And it's, we have a few things we do, but my answer to that question will kind of be largely depend on the problem that we are trying to solve, and it'll be different for each customer. But I talked about this digital twin building process, right? And this was something that came up way earlier on. Like without good quality data, this digital twin is not basically buildable. So how do you know that without actually undertaking the exercise of building this, how do you know if you have the right amount of data? So several approaches of solving this. Like step one, starting from the business, you make sure the sales get the right guidance, right? There is don't look at the sensor placement, look at the level of maturity you have with this customer. Are they, if we give them a feedback, do I ask to install a new sensor? Like the sensor will sometimes cost only $200 to install, and that will make a world of difference. Are they willing to do that? Is there existing data quality? Are you getting at least one data point in 15 minutes, every 15 minutes? Like this, so there are like fundamental checks that you can do, even by like a non-technical sales qualification process, or like even before you start thinking about model, start thinking about even data analytics on this. And then you only qualify, like in our case, we only qualify the customers who we think has like a certain initial quality check mark. And it goes into like domain experts. Domain experts are like, and these are there in every data science company. These are non-data scientists who are coming from the industry, right? In our case, this is water quality experts, wastewater industry experts. They have been taught a certain degree of data analytics, and they look at data, sensor placement, they apply all of this, their expertise to this, and they do an additional layer of filtering. Now, the first level of filtering is the cheapest. The second level, it starts getting expensive, but a data scientist is the most expensive hire you can make. Like, but we need to minimize the number of bad customers reaching data scientists. If you get filtered out earlier, that's better. So we equip them with like these non-programmatic tools like visually analyze data, things like that, that will ask for does the critical sensors have enough data? Are you seeing anomalies in critical sensors? Things like that, and they have another set of checklist. But sometimes some of the advanced data problems are only like figure out after you start building a model. You do some basic engineering, you do an initial model, and you realize that it's not fitting, doesn't work, right? So in there, what we have tried to do, and we are not fully successful in doing that, but as you gain experience over multiple projects there, you can accumulate this knowledge into like an AutoML framework that so let's say I pick a process of flocculation. Flocculation is like a big tank in which you add some chemicals and gets suspended solids that gets on top of this tank, right? So then there are various flocculation mechanisms, or there are various models that gets built for this to reproduce this problem. And we kind of build that in an AutoML framework in which like each model gets tried one after the other, and a certain degree of hyperparameter tuning is performed, a certain degree of feature engineering is performed on all of these. And this is automated. This is before a data scientist applies his or her intelligence to this process. The automated, you see whether like a certain degree of quality is even correlation is even possible. Like what's your MAP, what's your RMSE numbers, and this is before putting in like a lot of work from the data scientist, which means you can filter out a lot of things when you go through this set of steps. But sometimes things just pass through, and there were instances where we have spent the time and money only to realize that it just doesn't work.
And in those cases, you have to go back to the client and say, "Hey,
yes,
sorry.
Install the sensor for us." Well, no, we won't say sorry until we have given up on it. But at that point, we'll say, okay, can you get this more data? Can we wait a few more months? Can I collect a few more data before we can start modeling? Can you do this extractions on this? There are scenarios that we have not seen these systems operate in. So can you add a little more chemical, a little less chemical, and then it's all step testing, right? So then can we observe the resulting data points so that we can capture that dynamics in the models, like all kinds of things we do to improve the model building process over time. But ultimately, if none of that works, yes, you have to give up.
Mm-hmm. Wow. I find it fascinating, this idea of going through 3 different tiers to get to where you want to go. And I really like the way that you put it is the data scientists shouldn't be touching it because they're so expensive. They need to be focusing on stuff that we know actually works. And so first you get sales, they go through sales, then you have a subject matter expert that looks at it, that knows a bit of data analysis. And then if it passes through these filters, and then it goes through that AutoML to make sure that there's possibility on that end, and then it can go to the data scientist. So that is a really interesting way of going about it. I hadn't heard that one before. So it's nice to know. Now, my last kind of question for you, because I know we're getting close to the end. When it comes to, because you're doing a lot of sensor and you're doing a lot of Internet of Things, what are some specific MLOps problems that you feel are involved in when you have the Internet of Things and you're trying to work with that, if there are any?
There are many. So Internet of Things means like having some sort of sensors, and I still want to classify that further. These are all like time series problems, right? Time series data is what you're primarily dealing with. Well, not necessarily, but in our case we are. So, but I want to differentiate between like us and, for example, like companies like Tesla, who you'd think have the same issue, right? But in case of Tesla, they own the sensors, or they release the sensors, which means they get to keep this quality of data that they want. They keep to ask this quality of data and frequency of data that they want. But in our case, it's customers own the sensors, right? So it contributes to all these data quality problems we talked about, which we need to really enable data scientists and data engineers working on this problem to be like reproducible and essentially, reproducible. What else comes in? Then that's a IoT time series forecasting problem that's somewhat unique to us. There is also what we call as like causal models, or things that basically underlying has like a physics equation. For example, in this flow collation example I told about, there is like a certain degree of biological process going on in there, but as soon as you add a boatload of chemicals to it, like beyond your regular usage, the characteristics change, right? It's like you throw a ball over the air. Typically, you expect a particular trajectory. It goes and falls in effort. You can define that curve physics equation, but as soon as you throw another ball and then hit it, it changes its course, right? So these control system style models, and when that gets combined with IoT style problems, so like a pump, for example, you can turn it off and at will. Chemicals, you can add control chemicals to this flow collation aeration mechanisms. They all has the potential to change a normally defined characteristic or a normally defined equation of this process significantly enough that typical ML methodologies doesn't work. It's cutting edge, bleeding edge research field, data driven control, model predictive control, and we do some good stuff with it. But that's a largely data science problem again. Right now, the part of the MLOps is again where MLOps comes in. It's facilitating the reproducibility on this as well. Yeah.
Talk to me in the last couple minutes about this automatically retraining of the models and why you felt that was necessary.
Because of the number of models that goes through this pipeline, it's impossible for somebody to manually monitor and retrain as necessary. It's a dangerous territory. It's not easy to do. It takes a lot of time. But once you have deployed 5 pump models, the 6th one, you have a certain degree of confidence that it's new data and new patterns. All you need to do is like extra hyperparameter tuning. At that point, you can automate the retraining. But generally, I do not. It's not easy. It's not recommended until you reach a certain level of maturity with the model, or until you gain a certain degree of confidence with the models you have deployed in production. It works in fintech. It works in ad tech. It works for us, but took a lot of time and effort to build it. Things like fraud detection, for example, right? It doesn't work. It's not easy to do. Like you'll have to the patterns, the drift that those kind of models have are too behavior altering that same model itself. Like the neural architecture, for example, if you picked one, it doesn't work. You need to rethink what consumer behavior changed and rebuild it sometimes. But sometimes it works. In our case, most of the times the dynamics remain the same. A pump is a pump is a pump. Sometimes units change. Sometimes they operate more frequently. It's just more data. So retraining is more applicable to our use case.
What metrics are you looking at when you're retraining? Like when you're monitoring these models and it triggers a retraining, what is it usually that the metrics you're looking at to cause that retrain?
Yeah, so there is a human in the loop, by the way, right? It's automated enough to the point where you can do a click and it gets retrained. But the models generally emit all possible metrics it can. So RMSE, MASE, whatever you want to call it, depends on the type series model you're building. Other type of models have their own metrics, but you get to look at them and you have a threshold we set for each of those metrics at the point of training. And as soon as the threshold drops based on some sort of drift, that you'll see that you'll go beyond the threshold. It triggers an alert. It doesn't do the retraining, but yet triggers an alert, and then you can go and look at it and just click retrain, and then it does retraining. Right? It's automated, but it's not automated both at the same time. But getting to this point itself is a good exercise.
Yeah, that's so cool. Because I was going to ask that if there was anyone involved, and if you still had the human knowledge to be able to look at it and say, yeah, we need to, or maybe this is okay. We don't need to re-trigger this.
Yeah. It's minimal, but there is human involvement in every case now. I mean, I want to reach a point. Obviously, I want to reach a point where there is none. But it's going to take time.
Well, there is the idea of you can run into trouble if you start retraining models and you don't have it really down solid. Like you can retrain models without, and then you just keep retraining them, and it causes a bunch of chaos.
Yeah, absolutely. Yeah, I mean that happen all the time. Right? It's a little less prevalent for our industry compared to like a churn prediction model, like things like that change a lot. There are external factors that depends on it, but a pump is a pump.
Yeah.
Right. There is. I do think we can reach a point where where our retraining is more automated, but someday.
Yeah. Perfect. Well, this has been immensely insightful for me. I really want to thank you, Vishnu, and everybody that is still here listening. Hopefully you enjoyed it as much as I did. That's about it. I think we're going to call it a day here. Thanks for listening, and we will see you all later.
Thank you, Dimitri. It was really nice talking to you. And
see you, man.
Thanks everyone else.